In a previous video, I talked about how if you have, say, a loop of wire and then you have a magnet and you, say, move the magnet closer to that loop of wire, then what's happening is you're changing the magnetic field that loop of wire is experiencing. That change in the magnetic field is going to result in an induced current in that loop, and that induced current has its own magnetic field associated with it because you have a magnetic field when you have moving charge. So essentially what's happening is an oscillation of a changing magnetic field results in a changing electric field, because if the charge has an electric field and the charge moves, that electric field is changed. And then that changing electric field can produce its own changing magnetic field, which can produce a changing electric field, which can produce a changing magnetic field. You kind of get the idea here. It turns out that you can have energy go through these undulations of changing magnetic and electric fields. And if you've taken introductory physics, you've already learned about the idea of waves, such as waves in water or pressure waves in air, which manifest in sound. However, with those waves, there's something doing the waving. So for instance, in water, you have water molecules that are moving about in a periodic fashion. And so there's these undulations of peaks and valleys. And we call the time it takes to go from a peak to a valley back to a peak, we call that the period of the wave. And the number of cycles, i.e. peak to valley, back to peak, the number of cycles that you have every second, we characterize that as the frequency. And so there's an inverse relationship between the period and the frequency. So if you have a longer period, you have a lower frequency. And if you have a shorter period, you have a higher frequency, which is to say, like if you have a lower frequency wave, you have these more extended undulations, whereas if you have a high frequency wave, you have more rapid undulations. But again, we're talking water, we're talking about water molecules moving in this wave-like fashion. If we're talking about air, we're talking about undulations in air pressure propagating through air, and therefore allowing sound to propagate. But when we're talking about undulating electric and magnetic waves, you don't actually have to have stuff doing the waving. You can have a propagation of an electromagnetic wave through empty space, through a vacuum. Essentially what this undulation of electric and magnetic fields is that at a particular location in space, you can see that the electric and magnetic fields can change in that particular location. And it's because of this phenomena of a changing magnetic field manifesting in a change in electric field, which then manifests in its own change in magnetic field, and so forth. And so electromagnetic radiation is essentially how energy is carried in a wave-like fashion, where what's waving is this undulation of changing magnetic and electric fields. And so to give you a sense of if you have electric and magnetic fields and what direction the electromagnetic wave is going, this is where we get into the right-hand rule again. And so when I talked about the right-hand rule, I talked about a couple of different ways where if you have two different vectors and you want to multiply them, then what you need to do is what's mathematically called a cross product. And so while we're not going to make you actually do the vector calculus of a cross product, you can use this right-hand rule to get a sense of if you multiply one vector by the other, what direction the resultant vector is. And that resultant vector, by the way, in a cross product is perpendicular to the two original vectors that you crossed to get that third vector. And so in the case of electromagnetic radiation, you're going to have a direction of the electric field, you're going to have a direction of the magnetic field, and it turns out to figure out what direction the electromagnetic wave is propagating, we're going to take the cross product of the direction of the electric field by the direction of the magnetic field. And so there's two different ways in which you can do this right-hand rule. And so one way is to take your fingers and put that in the direction of the electromagnetic field. So let's say that the electromagnetic field was, say, going up. And let's say that the magnetic field is going to the side. So what I would do is I would take my fingers and I'd put them in the direction of the magnetic field. And then what I do is I curl my fingers in the direction of the magnetic field. So fingers in the direction of the electric field, curl into the direction of the magnetic field. And then the thumb, when you do that curl, is perpendicular to both of those directions, and it shows you the direction of the magnetic wave. And so in this case, it would be coming towards me, away from you. Okay, now if the magnetic field was, say, going this way, then I would have to take my fingers, put it in the direction of the electric field, and then when I curl it in the direction of the magnetic field, now it's going away from me, it's going towards you. So that's one way you can do it. Take your fingers, put them in the direction of the electric field, and then curl your fingers in the direction of the magnetic field, and your thumb will be pointing in the direction of the electromagnetic wave. So another way in which you can do it is you can actually start with your thumb and put your thumb in the direction. So let's say the electric field is going up, so I have my thumb going up. And then what I want to do is I want to put my fingers in the direction of the magnetic field. So let's say the magnetic field is going this way, electric field is going up. And so what I want to do is I'm going to have my thumb in the E direction, my fingers in the B direction, and the direction your palm opens up. This is the second way you can do the right-hand rule, is the direction. And so my palm is facing me, so the electromagnetic wave would be coming towards me and away from you. Now similarly, if the B field is going this way instead, then what I can do is I can take my thumb and go up, and now the B field is going this way, right? So I have to put my fingers in that direction. You see how my palm is now opening towards you, so it's moving away from me and towards you. So that's how you figure out, if you have an electric field and a magnetic field, what direction the electromagnetic wave is propagating. Now, it turns out that in a vacuum, because again, you don't have to have stuff waving for electromagnetic wave, it turns out that in a vacuum, the propagation of that electromagnetic wave is roughly 3 times 10 to the 8 meters per second. So 10 to the 9 is a billion. So 3 times 10 to the 8, that's 300 million meters per second. So to put that in terms of, say, something we're familiar with miles, that's 186,000 miles per second. Okay? So if you go around the Earth once, that's about 40,000 kilometers. And so if you have something that's moving at the speed of light, which is the speed of an electromagnetic wave in a vacuum, then in 1 second it would go around the Earth 7.5 times. Think about that. It would go around the entire circumference of the Earth 7.5 times in 1 second. That's the speed of light in a vacuum, and that's the speed at which the undulations of electric and magnetic waves propagate. So while in the case of electromagnetic radiation, you don't have to have any actual particles or molecules doing the waving like you do in, say, water waves or sound waves, you do have this mathematical wave-like relationship where you have these alternating peaks and valleys and peaks and valleys and peaks and valleys. And so the same wave mathematics applies, where you talk about a period as being the time going from one peak to a valley back to the next peak. And there's still an inverse relationship between the periodicity of the wave and the frequency. If you have shorter periods, you have higher frequencies. If you have longer periods, you have lower frequencies. And again, like this would be lower frequency, this would be higher frequency. You can also think of it in terms of energy. Like if you, say, had a rope and you wanted to get the rope to start waving, then you would take one end of the rope and you'd start going up and down. Like if you're going up and down slowly, you can imagine the wave in the rope is going to be longer than if you went like this. You put more energy into it, you'd have higher frequency. And the same is the case with electromagnetic radiation. The higher the frequency of the electromagnetic radiation, the more energy that you're talking about with the propagation of this electromagnetic wave. So it turns out that the universe is filled with electromagnetic radiation, and a lot of it we can't directly observe. Now, the electromagnetic radiation we're probably most familiar with is the visible spectrum. Okay, this is light that we can see with our eyes, and some of you might have heard of Roy G. Biv, which is the different colors of the visible spectrum: red, orange, yellow, green, blue, indigo, violet. And so those different colors, turns out, associate with different wavelengths and therefore different frequencies of electromagnetic radiation. And again, electromagnetic radiation is this wave-like undulation of changing electric fields, which change magnetic fields, which change electric fields, which change magnetic fields, and so on. And so it turns out, like in the visible spectrum, redder light is going to have longer wavelengths and therefore lower frequencies. And then as you move to orange, to yellow, to green, to blue, to indigo, to violet, you're dealing with higher frequencies and therefore shorter wavelengths. So blue light has shorter wavelengths and therefore higher frequency than red light does. Red light is going to have lower frequencies and longer wavelengths. But this is just the portion of the electromagnetic spectrum that we can see with our eyes. There's all sorts of electromagnetic radiation out there that is at frequencies that our eyes can't detect. But you probably heard of some of these things because there's other ways in which we can detect them, and there's also indirect effects of them. But just to kind of put it into perspective of how you have this spectrum of energy, and that energy is traveling in the form of electromagnetic radiation with different wavelengths and therefore different frequencies, we can start with, say, the lowest energy that we might be familiar with, say radio waves. Okay, radio waves are going to be much longer in wavelength and therefore much lower than frequency than, say, way over here where we're dealing with, say, gamma rays or X-rays. You might have heard of those. You probably heard of X-rays in terms of the context of medicine. So X-rays are going to have way, way, way higher frequency and therefore way shorter wavelength than, say, radio over here. Over here would also be something like a microwave. Microwave is going to be of lower frequency and therefore longer wavelength than, say, X-rays or gamma rays. Now, as we get closer to the electromagnetic spectrum, you might have heard of infrared, okay? Maybe like infrared night vision goggles, which is essentially looking at like heat that's radiating. And so infrared is going to be of lower frequency and therefore longer wavelength than, say, the visible spectrum. And then as you go to even higher frequencies past the visible spectrum, you get into what's called ultraviolet. You might have heard of that. And so some like radiation from our sun is in the form of ultraviolet radiation. That's why you would wear, say, ultraviolet sunglasses. Okay, so it turns out that the wavelength of the visible spectrum, the red, orange, yellow, green, blue, indigo, violet, that ranges from about 400 nanometers to 700 nanometers in wavelength. Okay, and so, by the way, a nano, 10 to the minus 9, okay, 1 in 1 billion. And so it turns out that the redder light, as I mentioned, is longer wavelength. The bluer light is lower wavelength. So 400 to 700 nanometers is essentially 400 nanometer wavelength. It's going to be your blue light, and then it goes all the way to red, which is 700 nanometers. But again, this is just, I keep doing this because this is just a portion of the electromagnetic spectrum that we can see. As you move further away from what we can see, you're going to deal with even higher frequency phenomena like ultraviolet, X-rays, and gamma rays, or you're going to deal with lower frequency phenomena like infrared, microwaves, and radio. And so just to sum things up, electromagnetic radiation is a wave. It's a wave where at a given point in space, you're going to have undulations of electric and magnetic fields. Changing electric fields can change magnetic fields, which then change electric fields, which then change magnetic fields. There's a mathematical wave-like property to this, and that wave-like property is such that these waves repeat themselves. That's what I mean by undulating. And the rate at which they repeat themselves is essentially the frequency of the wave. Higher frequencies are going to deal with higher energies. Lower frequencies deal with lower energies.